portion, our afternoon session at FSI. Starting us off will be Matt introducing our first group.
All right, it's my privilege to introduce our next presenters. We have Dheevena and Shalika, and their project is titled Synthesis of a Novel Anti-Tumor Drug, 4-methyl Phenyl-N Acridnyl Hydroxylamine.
Good afternoon, my name is Dheevena, and I'm Shalika. And for the past 6 weeks, we have been researching the design and synthesis of 4-methyl Phenyl-N Acridnyl Hydroxylamine.
So our compound is a novel anti-tumor drug. In addition, it is also a 9-amino-acridine derivative and a catalytic inhibitor and a 9-amino-acridine derivative. Those will be explained in the following slides. Our goal with this drug is to make it less worse than other chemotherapy drugs. So we basically want to reduce the side effects of this chemotherapy drug. And we hypothesized that we can do this by making it less susceptible to hydrolysis. Hydrolysis is when the water in your body breaks down the drug or compound and makes them not working anymore. We think that by making this drug less susceptible to hydrolysis, that it can stay in your body for a longer time and work for a longer time as well.
So why is synthesizing drug in the first place? Cancer is one of the leading causes of death in our society. It is the uncontrollable growth of abnormal cells in the body. These cells group together, forming tumors in different places, such as your breast or your lungs. In 2017 alone, 1,688,708 people are estimated to be diagnosed with cancer. And to make it even worse, 600,920 of them are estimated to die of cancer. However, there are 3 main treatments to cancer: surgery, radiation therapy, and chemotherapy. Surgery is just the eradication of large tumors in the body. It may not be so helpful in the beginning stages of cancer, however, it can be a lot more helpful in the more severe cases. Chemotherapy is just a decreased rate of replication of the cell. However, it is inducing the drug into your body, so it has severe side effects. Same with radiation therapy, which is just the targeted energy to shoot tumors and kill cancer cells. Due to all of these having severe side effects, our compound is trying to have the same effect on these that the 3 main treatments have with less side effects.
So some background about our compound. Our compound is a chemotherapy drug, and chemotherapy drugs work by affecting the cell cycle. The cell cycle is when the cell is replicating, so it's basically mitosis or meiosis. There are 2 types of chemotherapy drugs: cell cycle-specific chemotherapy drugs and cell cycle non-specific chemotherapy drugs. Cell cycle-specific drugs work by affecting the cell during a specific time during cell replication, and cell cycle non-specific chemotherapy drugs work by affecting the cell during any time in its life period, so while it's resting or during replication. Our drug is a cell cycle non-specific chemotherapy drug. DNA replication. In order to understand how our drug works, we must look at it on a molecular level, and we must also understand the process of DNA replication. So what is DNA replication? DNA replication is the process of when DNA replicates to prepare for cell division, also known as mitosis or meiosis. It all starts when an enzyme called heliophase enters the cell and binds itself to the DNA. The heliophase starts unzipping the DNA strand into 2 separate strands, so the DNA polymerase can enter and create complementary strands. Thus, as the DNA heliophase is unzipping the DNA strand, the DNA becomes more and more tightly wound. In order to prevent this coiling, another enzyme called DNA topoisomerase enters the cell and unwinds the DNA. If you inhibit the topoisomerase or stop it from working, then the DNA cannot replicate, and therefore the cell cannot replicate, and it will go into cell death, also known as apoptosis.
Our drug falls in the category of being a DNA interpolator, which is just a substance that inserts itself into the DNA itself. To be more specific, it inserts itself in between DNA bases. Stop the topoisomerase enzyme works. To be more specific, there are 2 types of topoisomerase enzymes, type 1 and type 2. Type 1 works it breaks off one strand of DNA and unwinds it around the other. However, topoisomerase 2 breaks both apart and unwinds them around each other. But topoisomerase 2 also goes back to a repair that DNA strand. Our drug stops that reparation, sending it into a programmed cell death, also known as apoptosis. It also acts as a catalytic inhibitor, which means that it can stop the replication process through the end part of the cell cycle. The base of our drug is based off of a 9-amino acid compound. Our compound acts as an anti-tumor property, which we have described before, such as being a Dheevena intercalator and a catalytic inhibitor. It means that it can, again, once again, stop it during any part of the cell cycle. Due to it being a catalytic inhibitor, it has been tested in rats due to the rats having very similar DNA structures. Little has actually proved that they have catalytic inhibition properties by examining it in other derivatives of 9-amino acid compounds, such as the compound that Shalika and I have been synthesizing and compounds that cell have been synthesizing in other derivatives.
Phenyl-N Acridnyl Hydroxylamine. This is a compound that's being researched by Massachusetts currently. Our research has come off of this research. Our compound is actually a derivative of this compound, but our compound has an extra methyl group. We have gotten most of our methods and processes from the research from this compound. For step 3, there are 3 possible procedures. We looked at the first and third procedure, but decided to go to the second one due to the availability of compounds and time.
So other derivatives based off of Massachusetts compounds could include adding an extra electron donating to the compound or an electron withdrawing to the compound. An electron withdrawing group would include the localization of the electrons around the 9-amino acid compound, causing the bond between the compound and the phosphate group to be stronger together, meaning that the cells send the cell into programmed cell death a lot faster and easier. However, the methyl group that we are attaching is an electron donating group. This electron donating group will shift the electrons in the electron cloud, causing a repulsion between the phosphate group, which is negatively charged, and the compound, which is also negatively charged, to be stronger, allowing it to break off easier. This means that if the compound affects the normal cell, which is what we are expecting, the cell may be able to overcome the compound, causing it to replicate normally. However, if it affects a cancer cell, it will cause it to go into programmed cells. So what is a methyl group? A methyl group is just an extra CH3 attached to any compound. It can be an electron donating group, which we just described, and it is a catalytic inhibitor and stops them to work from where it's placed. So this compound over here is a compound that Matthew himself has been synthesizing, and this is a compound that Shalika and I have been synthesizing. The difference can be seen in this very top methyl group that we have attached. When I talked about the electron cloud, I talked about the localization of the electron. So the electrons in this cloud would follow the path of and distribute themselves around this 9-amino acid compound, causing it to change the repulsion based off of the phosphate.
In order to synthesize the final compound, we have split up the methods into 4 main steps. So step 1, the synthesis of the dihydrogenous salt. In order to begin this first step, we got a 25 milliliter groundwater flask out of the oven and put a stopper on it and inserted argon gas into it. The argon gas is basically to create inert atmospheric composition. It basically keeps the humidity out of our reaction and makes sure that no water molecules interfere with it. Then we got P-iodotoluene, diachloromethane, and TFOH acid and added it to our compound. We let this compound into our flask and left it to stir for 10 minutes. After that, the compound turns this dark green-brown color. Next, we use a rotary evaporator. A rotary evaporator is a machine that separates the solute from the solvent. Once we use the rotary evaporator, our compound turns into this dry powder that was sent to the outer rim of the flask. In order to get the compound off the outer rim of the flask, we use another compound called diethyl ether. We rinse our compound with diethyl ether and let it sit in the fridge for about 30 minutes. In this first step, we can see the acrid TFOH being inserted into our flask. In this second picture, is our groundwater flask in the machine with the rotary evaporator. And in this third picture, we can see our compound after it was rotary evaporated. As you can see, the outer steps, the outer rims of the round bottom glass.
Once the dilated Acridnyl tricycle is synthesized, we then move on to synthesizing the N-formyl phenyl-N balance. In order to do this, we took a different 25 milliliter round bottom glass, placed it in the hood with a stopper on top, and inserted organic gas to create these inner active conditions to keep the water vapor from reacting our compound. And then we added DMS, TBUOK, hydroxylamine, and the diarylated tricyclate, which we synthesized in step 1. Once this was completed, we then heated the solution to 60 degrees Celsius and allowed it to stir for 1 hour using a heating method. Once this was completed, we then moved on to separating the non-organic layer and the organic layer. In order to do this, we added the solution into a separate funnel and then added ethyl acetate in the ionized water. Anything in the solution which was non-organic would then be dissolved into the ionized water, and anything that was organic, which is what we wanted, would dissolve into the ethyl acetate. Once we added these components, we then shift the separatory funnel in order to allow the compounds to dissolve, which then we then allowed it to sit in order to separate into layers. Due to the non-organic layer having a higher density, this caused the layer to come on the bottom while the organic layer was on the top, allowing us to eradicate the non-organic layer into a waste paper. We did this step several times. However, during the last repetition, we used a brine solution in acid, which is a very, very saturated saltwater solution, in order to distinguish and make this non-organic layer in order to definitely get rid of all the non-organic compounds. Once this was completed, we added anhydrous sulfate. Anhydrous sulfate, when added, will absorb any water particles in order to take out the last bit of deionized water which we added. And then we set up a gravity filtration system in which the anhydrous sulfate and the water particles would be filtered through into the filter paper, leaving us with the ethyl acetate and the N-formyl phenyl-N balance. However, we still have to get rid of the ethyl acetate. And so next, we moved on to placing the solution we had into a rotary evaporator. Then we rotary evaporated it at a low enough temperature in which the ethyl acetate evaporated, leaving us with N-formyl phenyl-N balance. In this first picture, you can see our gravity filtration system set up. The anhydrous sulfate and the water molecules would have been stuck in this filter paper, leaving us with the N-formyl phenyl-N dissolved in the ethyl acetate in the round bottom glass. And the second picture was taken after the rotary evaporation was completed, in which the ethyl acetate evaporated, leaving us with N-formyl phenyl-N.
Step 3, the hydrolysis of O4-methylphenyl hydroxylamine. So in order to start this step, we once again got a 25 milliliter round bottom glass and inserted it with argon gas. Then we had a 4 milliliter 1:2 ratio of methanol and chloroform added into our flask, and the stir bar was turned off. Once that was over, we added potassium carbonate and hydrochloride into the flask and let it stir for a couple more minutes. After that, we added our product from step 2 into the flask and let it stir for 15 hours at room temperature. By then, our compound was a tan-colored brownish tube. And then the next step would be to filter it through a citrus glass tunnel with diethyl ether. Next, we would have absorbed it with silica and washed it with 100 milliliters of the 20 to 80 ratio of ethanol and pentane. Next, it would be rotary evaporated, and we would have produced a yellow, oily substance, which is O-phenyl hydroxide. In this first picture is our round bottom glass when the first 2 compounds from this step have been added. And in the second picture is our compound after the compound from step 2 was added. And step 4, the synthesis of O4-methylphenyl-N Acridnyl hydroxylamine. For this final step, we use molten phenol and dichloroacridine and put it into a 25 milliliter round bottom glass and let it stir for a few minutes. And then we would have gotten O4-methyl Phenyl-Hydroxylamine from step 3, and we would have added it into our round bottom flask. And then we would have stirred it at 80 to 100 degrees Celsius for 6 hours and let it stir with the sun. And then it would have been cooled to room temp, and 50 milliliters of CH2Cl2 would have been added into our round bottom flask. Next, the sodium hydroxide and the compound would be added into a glass bottle and would be separated in order to get the phenol out of the mixture. Then it would have been gravity filtered and photographed, and the final product would be O4-methylphenyl-N and Acridnyl hydroxide. Results. So during the past 6 weeks, we have not completed step 4 or step 3. We have only been able to do step 1 and 2. Step 3 was attempted, but we could not finish it due to limited time and limited material. So we don't have any results for step 3. And steps 1 and 2, we've done it twice, so we have 2 trials. The first trial was not significant and it wasn't pure enough, so we did it again. And after the second attempt, we tabulated our percent yield to be about 80%. And we did this by measuring the compound in the glass and then taking the compound out and measuring the glass. And we got 0.02 grams of the compound.
So this first patient model was taken after our first attempt at synthesizing the product in step 2. You can see several of the keys correspond to the hydrogens in our compound and the solvent we used, which was chloroform. So the very large piece, which means 78 ppm in chloroform, which is good that it showed us that we engaged in the work. However, several of the keys are extras, and so it shows that there are present impurities in it. In our second HMR, we could identify several of the keys to correspond with our hydrogen, and they also follow the electronegativity rule in literature against the keys with the chloroform form, and also we could identify the levels we attached. However, the way in which this HMR was taken is different than the first attempt. For this one, we took the chloroform and directly added it to the bronzone flask, causing the solution to be very, very concentrated with our product. And so due to the peaks being very small and short, this tells us that the product that we wanted in the solution was very, very low. And so even though we had a very high percent yield in 80%, several of it was due to impurities and human errors. So future studies. Since we only had 6 weeks to do this research, we did not get to complete it. However, if in the future it can be successfully synthesized, there's a long process it goes through before actually being used as an anti-tumor compound. First off, it will be set into a professional lab setting in which higher yields, precise production of the drug, and production in large amounts would be pushed for. Next, it would then be tested in infected state cells of plate cells, in which it was tested to be in the side effects where it's as expected, or if any of the side effects form that we do not expect. And if that goes successfully, it would then move on to being tested on rodents, such as being tested on mice and rats, which I know several other groups are doing. And if that goes well, it would then be tested in small mammals, such as dogs and cats, next onto primates, and then next to the clinical trial. However, this process does take a very long time, as in it could go up to decades.
Conclusion. So although we have not synthesized the complete drug and it has not been synthesized yet, and we haven't gotten up to step 4, after completing step 2, we realized that we had higher yields than we hypothesized. We hypothesized we get around 56% yield, and we got about 80. And although all of it's not a pure compound, we realized that the drug can be synthesized in inert and specific conditions created in a specific lab setting. So our conclusion was that basically that this drug can be synthesized with minimal human error under specific and inert conditions.
Acknowledgement. We would like to thank the Union Pacific Foundation for funding our research here over the 6 months.
I would like to thank 15-mile marriage for sponsoring me at this wonderful time at FSI.
And then I would like to thank the Dheevena Foundation for funding my research and participation.
We would like to thank Matt himself for advising us and mentoring us through this wonderful research project.
I'd like to thank Shalika for also co-mentoring us in our research project.
In addition, we would like to thank Len Schottler and Scott Newberg and everybody else who helped us in this.
And lastly, we would like to thank Computer Science Institute and Lori Hall for allowing us to see the learning. Thank you for listening to our presentation. We can now take any questions.
What would you anticipate would be the time and the resources needed to complete all the way through step 4?
So I think we could have actually tried to see this in step 4. It's just that the product after step 2 can be bought or can be made, and one of our goals for this project is to make our drug accessible to all demographics, so we didn't want to use money to buy it. So it's possible that it could be made to step 4, but it just wouldn't be 100% pure.
Also, the product of step 3 can also be commercially bought. However, we did not complete our step 3 because we didn't have the materials and resources in the amount of time we had. However, if we did have more time and more trials, like we being last patient in March, we would be able to hopefully get a higher yield and a pure version of the compound.
So in the past 6 weeks, you guys successfully got this first one too. Assuming you had a little bit of time on your resources, how much longer do you think it would take you to go all the way to step 4 successfully? Well, the question was, how long do you think it would take you to go through step 4 successfully? I don't think we can say a definite amount of time because there's a lot of human errors that could have been made in the lab. But I feel like it could have been done just not in the 6-week time period that we had.
Maybe like another few weeks, but for the higher yield, that we definitely would have gotten a low yield if we got through step 4, because in previous research done on this compound, the yield for it was around a little less than 50% actually, and so we pushed those through the compound.
So you said there's a previous research on how was your guys' project?
So as we said before, ours is mainly based off of that compound, and we talked about how to add other like electron donating groups or electron withdrawing groups, and the other half of our research group added the electron withdrawing, so we went with the electron donating. But there are other research papers talking about the electron donating and how, which is where we got our ideas from. Right.
So how common is it, like, handling drugs in, like, the cancer treatment market? Like, is it a common drug that is, like, prescribed or given to patients and, that we're going to?
So the question was how common this drug is and like how often it's used and if it's prescribed or not. Well, our drug definitely, so we went into this research project knowing that this compound is very new and that if we were to synthesize it, we'd be the first ones to get it done successfully. So no, it's not really common. However, there are other types of drugs which work as DNA circulators and affect how the same effect does it. We're just hoping this has no side effects. And there are other drugs with the same base compound, so non-amino derivatives of drugs.
Why did you say a electron donating group?
Well, so we chose to do an electron donating group instead of the electron withdrawing group because in the background research, the electron withdrawing group did have a longer synthesization time and had a lot more background information on what the methyl groups do. However, we also decided to do methyl groups because of the effects it would have on normal cells, causing the reverse bond so that it would affect normal cells, hoping that it would have less side effects in the bond.